Hi everyone, thank you for coming to watch this Canadian Academy Physics video. In this video we're going to be talking about nuclear physics, and we're going to start that off by covering the composition of the nucleus. And so if you saw our quantum physics video, then you're well aware of Rutherford's gold foil experiment. But in this experiment, he determined that there's a small sort of central and positive core to every atom. And this positive core is termed the nucleus. And so we know that the approximate size of the nucleus is in the order of 10 to the negative 14 meters, which is actually 10,000 times smaller than the atom. And as we already know also is that every nucleus is composed of a certain number of protons and neutrons, but we can collectively refer to protons and neutrons as nucleons. And so each of these nucleons is held together by a nuclear force. And so what's interesting about this nuclear force is that it's very attractive at distances of 1 femtometer, which is 10 to the negative 15 meters. But whenever you consider distances less than 0.7 femtometers, the forces that are experienced by the protons and neutrons are actually repulsive. So whenever you see a sort of model like of a nucleus, there's actually a significantly small space between each of these protons and neutrons, and that's because of this repulsive force at the same time as they are all attracted to one another. But nuclear forces are independent of the charge of these particles, and so that means that a proton to proton or a neutron to proton or a neutron to neutron interaction will all experience the same magnitude of attraction to one another. And so next we're going to talk about nuclear notation. And so the atomic number is the number of protons in an element, and the number of protons actually determines whatever element you're considering. And so we can denote the atomic number by the letter Z. And so the mass number is denoted by the letter A, and the mass number corresponds to the total number of protons and neutrons or nucleons inside an atomic nucleus. And so not surprisingly, the mass number does determine the mass of the element. And so whenever we combine these, this is what you'll likely see, where X is the element in question, A is the mass number, and Z is the proton. And N here is actually the number of neutrons, which we can get from subtracting the number of protons from the mass number. And so an example here of this combined notation is uranium-238. We have the mass number in the top left as a superscript, the 92 protons as a subscript to the left, and the number of neutrons as a subscript to the right. So what I want to talk to you briefly about is isotopes. And isotopes you've already likely seen in chemistry, but it's whenever you have a same element, so the same number of protons in a nucleus, but the nucleus has a different mass in comparison to one another. So below, in this example, we have 3 nuclei of strontium, and we know that each of these are strontium because we have the same number of protons, which determines the element in question. But the difference here is that each of these strontium nuclei have a different number of neutrons, and so accordingly we have a different mass number for each. And so these are all known as isotopes of one another. And so next we're going to talk about something that Einstein showed us. And so he showed us that mass is actually another form of energy. And so mass energy can be converted into other forms of energy. And so Einstein's mass energy equivalence equation that he derived is E is equal to mc squared. And I know all of you have seen this. This is arguably one of the most famous equations in physics, where E is equal to energy, change in m is equal to the mass defect, which we're going to describe next, and C is the velocity of light in a vacuum. And so what I want to introduce to you is the nuclear binding energy. And so if you consider the sum of the masses of neutrons and protons form in a nucleus, this sum of the masses is actually more than the actual mass of the nucleus. And so whenever you have a difference in the mass, then you're going to have this mass defect. And so this is what it's described as. And so if you have a certain number of neutrons and protons that are brought together, that are bound to form a nucleus, then that requires a certain amount of energy, and this is known as the binding energy. And so this binding energy of a nucleus may be defined as the energy equivalent to the mass defect of the nucleus. And so if we are to separate this nucleus once again into its nucleons, we just bound it together, but if we wanted to separate this nucleus, a total energy that's equal to the binding energy must be supplied. And so this is demonstrative of the law of conservation of energy. And so what we're going to talk about next is radioactivity. This is the nucleus. Here is radioactivity. And so radioactivity is a spontaneous nuclear phenomenon by which an unstable nucleus undergoes a decay. And so this results in the emission of some particles and electromagnetic radiation, specifically gamma rays. And so first, before we get into the types of radioactive decay, we're going to introduce the properties of these alpha and beta particles and gamma rays. So alpha particles, we know from the quantum physics video, these particles were used in the gold foil experiment, that they are positively charged and they contain a mass that is equivalent to the helium-4 nucleus, and they have a charge that is equal to the charge from 2 protons. And so beta particles, there's actually two of these, two types of beta particles. One is the negatively charged high-speed electron, and the second is the positively charged high-speed proton. And so we denote these separately. B plus corresponds to a positron and B minus corresponds to the electron. And so lastly, gamma rays. And if you imagine the electromagnetic spectrum, then you know that a gamma ray has the highest energy and frequency of electromagnetic radiation. And so the first sort of radioactive decay that we're going to discuss is the alpha decay. And so the alpha decay is just simply the emission of an alpha particle, which we can relate to a helium atom or a helium nucleus from the radioactive nucleus. And so the type of transmutation that this is undergoing is a large nuclei of one element is becoming a smaller nuclei of a new element. And that's because if we consider this element here, whenever we emit an alpha particle, we're basically getting rid of four particles for the mass, and we're getting rid of 2 protons essentially. So that's why this new element that we're creating here has a mass number that decreases by 4 and an atomic number that decreases by 2. And so what I want to introduce to you also very briefly is the disintegration energy, or you might have seen this as the Q value. And this disintegration energy is the difference between the initial mass energy of whatever's in question and the total mass energy of the products in a nuclear reaction. And this can also be defined as the change in kinetic energy during the reaction, because in order for a spontaneous decay to occur, the total mass of the decay products must be less than the mass of the initial nucleus. And so this difference in mass appears as kinetic energy of the products, and that's why we can say that the Q value is actually the change in kinetic energy. And so we have sort of an equation here, and that's using the same we're using the same nuclei from earlier here. We have X, Y, and the helium atom, or the helium nucleus, or the alpha particle. And so the disintegration energy, this difference, is equal to the initial mass energy of X minus the total mass energy of the products, which is the mass energy of Y, the new nuclei formed from the new element, and the mass energy of the alpha particle. And so whenever we have a positive Q value, that's going to correspond to an exothermic reaction, which releases energy, and vice versa. Whenever you have a negative value for Q, then it's going to be an endothermic reaction where energy is absorbed. And so the next sort of radioactive decay that I want to talk to you about is beta decay. And this occurs when you have the spontaneous emission of an electron or a positron. As we know, both of these are beta particles. And so this emission of an electron or positron is accompanied by the emission of an antineutrino or a neutrino, respectively. So an electron, whenever that is emitted, you have the emission of an antineutrino. And the opposite is true. Whenever you have the emission of a positron, then a neutrino is emitted. And the antineutrino and neutrino are both just neutral particles with approximately no mass. And these are emitted to conserve momentum in the system. And so what you need to know about beta decay is that the mass number remains the same. So we have a beta minus decay, which corresponds to an electron, and we have the beta plus decay, which is the positron. And we have two examples of that. So in this first example, we have a phosphorus nuclei with 15 protons, and what's actually occurring in the beta decay is that a neutron is being changed to a proton. And so that results in an increase in atomic number by 1. And so that's going to, whenever we're changing the number of protons, then we're then we're going to change the element in question. So this phosphorus nuclei is actually going to become a sulfur nucleus, and so this beta decay is accompanied by the emission of the electron and an antineutrino. And so whenever we consider the beta decay by a positron, we have here a sodium nucleus. The proton in the sodium nucleus is actually being converted into a neutron. So that's why we see a decrease by 1 in the atomic number. And so this is accompanied by the emission of a positron and a neutrino. And so lastly, we have gamma decay. And the gamma decay is actually the emission of a gamma ray photon from a radioactive nucleus. And so similar to an atom, a nucleus has discrete energy levels, and so this nucleus also has a ground state and an excited state. And so what's very important for gamma ray decay is summarized in this box, and that says a nucleus in an excited state will spontaneously decay to its ground state, and when it spontaneously decays, it's going to emit a photon with an energy that is equal to the difference in the two energy levels of the nucleus. And so in this diagram, we're going to put some context to these words. The energy from the emission of a photon is going to be in the order of kilo electron volts to mega electron volts. That's just something that we want to note. But what we have here is cobalt with 27 protons. So whenever we have a beta minus decay, then we know that a neutron is going to be changed into a proton. So that's going to result in nickel, which has 28 protons. And now that the nucleus is in an excited state, so it wants to decay to the ground state. And so in order to get there, it has to emit a photon, and this energy of the photon is equal to the difference in these two energy levels. And so once again, we're not at the ground state yet after the first emission, so we're going to emit another gamma ray, and that has a photon with the energy equal to the difference in these two levels. And so what we end with is no change in the atomic or mass number from where we started. So we started with originally we started with the beta decay, but in considering the gamma decay, we are not changing the mass number or the number of protons from start to finish. And so lastly, what I want to talk to you about just briefly is decay rate and half-life. And decay rate, the equation is negative r is equal to the number of decayed nuclei over the change in time. Or this is also equal to the negative decay rate times n, which is the number of atoms left undecayed. And so we can solve for n with this equation here, where we have n initial is the number of radioactive parent nuclei times e to the negative decay rate times t. And so this is a little bit better illustrated in this graph here, where we have the number of radioactive nuclei on the y-axis and the time on the x-axis. And as you can see, at the half-life, at the time of the half-life, we have exactly half of the number of radioactive parent nuclei. And so I'm sure most of you have seen half-life before in chemistry, but this is the time during which half of the number of atoms present initially have decayed, represented by T1/2. So the equation for the time for half-life is equal to ln2 over decay constant. And after a certain number n of half-lives, the number of atoms left undecayed can be given by this equation here. And this is the final equation that we're going to cover. N is equal to initial number of radioactive parent nuclei times half of the number of half-lives. So in this video, we covered the fundamentals of nuclear physics.